master's session actually, brainstorming session, rather I would say. Understandable. That is very serious and very active actually. Okay, so Sam will be joining us in 2 minutes. Okay.
Hello. Hello.
Morning, sir. Morning.
Oh, good morning. I'm sorry for the 5 minutes
Very good
delay
morning.
because we had a technical issues.
No problem, sir. No problem, sir. No problem, sir. Sir, so first, let me introduce yourself, sir. Okay, and then after you start your session, sir. Fine. So, with your due permission, I'm introducing you, sir. So, good morning to all the dear participants, and a very good morning to Professor Sanjeevi Kumar, sir. So, Professor Sanjeevikumar is an senior member IEEE, and he is fellow Institute of Electronics and Telecommunication Engineering. Professor Sanjeev Kumar received his bachelor degree and master's degree from the University of Madras, Puducherry University in the year 2002 and 2004 respectively, and later he completed his PhD from the University of Bologna, Italy in the year 2012. His field of expertise includes power electronics and drives, multi-phase machine, multi-level inverter, DC to DC converter, application of renewable power generation. He has authored 250 plus scientific research paper and has received the Best Paper Award from the IET and 5 Best Paper Award from uh, Electrical Engineering Springer book series. He has served as an associate editor and editor in different reputed journals. So, ladies and gentlemen, please welcome Professor Sanjeevi Kumar from the University of Aarhus, Denmark. Thank you, sir. Thank you. Over to you, sir.
Thank you very much for your. Could you able to hear my voice? Could you able to hear my
Yes, sir.
voice
Yes,
clearly?
yes, sir.
Okay.
Yes, sir. Yes, sir. Voice as well as the PPT also is visible, sir.
Thank you very much for your brief introduction. Today I'd like to present some what we have developed and what we have been doing for the long time in the field of electronics. We like to share our experience, what we gain. So for the future, definitely Uh, the power electronics play a critical role in electric vehicles because the goal of most of the nation or the global perspective is by 2030 to minimize carbon emission by 30% to 40% in Asia. In case of Europe, it is a goal to have 78% reduction by 2035 and 2050. The global scenario is focused on carbon emission by 100%. So transportation is a major area which makes the pollution to the environment either by roadways or sea transportation or space transportation, whatever the means, the vehicles creating the more emission when compared to other factors. And about the objectives, I will show you some various types of EV technologies and starts with the basics. And most important is about the energy sources, what are the charging techniques and impacts, and about today, most important, the EV market is dominated by Nissan and Chevrolet and Tesla. Still now, there is no 100% efficient electric vehicles. Along with, there is always a competition from China. BYD Automobiles is a very good competitor. With cheaper price, they are manufacturing many electric vehicles. So in this case, the most important is what are the types of electric vehicles? Who decide it? So the category or classification of electric drives is formulated by International Electrotechnical Commission, Technical Committee 69, which is also called as electric road vehicles from the United States. And they have 4 different classification. How they decided based on energy sources, storage, and what power electronics converter is used. So in this case, we are having 4 types: battery electric vehicles, hybrid electric vehicles, plug-in electric vehicles, and the future is going to be fuel cell electric vehicles. About battery electric vehicles, obviously the capacity is limited because it goes up to maximum 250 kilometers or maximum 300 kilometers in one charging. Maybe for the top tire it can go up to 500 kilometers, but it is not having a very high power propulsions, means to have a huge transportation capacity. And the big problem is we don't have a vast infrastructure on battery charging units, and minimum requirement for the charging is minimum 25 minutes to 30 minutes for one charging period of the battery when it becomes drained. So in this case, we need to have a fast charging networks, and of course to replace all the conventional pump station into electric vehicles, which is a very expensive part, but still it is useful for domestic applications like home application. We can have a good electric vehicle. In this case, Nissan and Tesla are the highest selling companies in the world. Again, the competitor is from China, BYD. How an electric vehicles play a critical role with the power electronics, which is very important because we have the battery banks, lithium batteries, which is connected to a inverter. The inverter will convert the DC to AC, and the electrical machines, either it can be a induction motor or synchronous machine or any special purpose. For example, depends on the cost of the electric vehicle. Nowadays we are moving towards brushless DC machines, synchronous machines, because more finite control, and there won't be any sort of slidings, etc., when we are driving at the hills, etc. So in this case, special motors are required. They are driven by a standard inverters. Then this is coupled to a single speed gear for transferring the electrical energy to the mechanical energy as a propulsion to the differential wheel, either on the front end or fore end of the vehicle. Next topic is on hybrid electric vehicles. Hybrid electric vehicles mostly used in urban areas because they are a combination of conventional petrol engine or diesel engine along with electrical parts. So in this case, we have different mode of operations. During the starting, the energy available from the electric motor, because of the rotation, we can power back to the battery and we can store the energy. During the stop condition, battery cannot be powered from the electric vehicle. It has to be powered from the grid or through external source of stored energy. Whereas in case of passing, the battery can pump the power to the electric motor for the propulsion. Of course, parallelly, IC engine, which is driven by the fuels, petrol or diesel, can pump the power and can be combined together to the powertrain. So it's a combination of both batteries and IC engine. During the braking, that's most important because we will have a frequent braking. So when we are applying a braking, obviously the electric motors are getting regenerative braking. So the power generated from the regeneration mode will be returned back to the battery and we can store the energy. During the cruising, of course, the propulsion system will be continuous and the main power supply is from the IC engine, which propels the powertrain of the electric vehicles. So under the propulsion period, we can able to get the energy from the motor and we can store in the battery and it can be used during the peak demands. Next point is a plug-in hybrid electric vehicle. So plug-in hybrid electric vehicles are again a combination of IC engines and of course batteries, but the capacity of battery is very large when compared to HEV, I mean hybrid electric vehicle. So in this case, the capacity of the battery is very large, so obviously the cost will be very high. And the challenges here is we have two different modules. One is a mechanical part, which is an IC engine, and battery is a electrical part with electrical motors. So combining these together with energy management is a very big challenge for the EV companies. And for example, in this case, a plug-in electric vehicle is dominated by Chevrolet's Toyota as a very popular model in all over the countries, particularly in EU and of course in United States. In future, it will be available in India too. And about a fuel cell electric vehicle, which is going to be the future because we can't able to replace IC engine absolutely by or 100% by the battery, because it can be good for a commercial based home applications, but not for the transportation, because transportation we need a large power and the power requirement by the electric vehicles cannot be compensated by the batteries, because batteries are very expensive and frequent charging is required. So in this case, fuel cell can be a good replacement for conventional fuels. In this case, they can also parallelly compared with the operation of batteries and fuel cell, because so that we can balance the power. So hydrogen, as a simple concept, hydrogen storage tanks needed to be developed, I mean the pumping stations. Then the hydrogen pumps can be stored within the vehicles in the cylinders. Then through fuel cell we can able to generate DC power. But the DC power generated from the fuel cell are not sufficient enough to drive or to power the entire vehicle. So we need to have power electronic circuits which can enhance the power and high efficiency. So in this case, air is available from the external means and the hydrogen is available within the vehicle. So the fuel cell can be able to generate the DC power supplies. And most important is the expansive, because we don't have a vast establishment of hydrogen power generation in frequent stopping locations for recharging, charging the fuel. So it's going to be a challenge for developing hydrogen fuel station with low cost infrastructures. Because if you use a conventional engine, it's going to be like $50 per kilowatt. Whereas if you're going to use fuel cell, it's going to be $200 per kilowatt. So it shows the difference, how much is the expense when compared to IC engines, petrol engines. So we have to find an optimal solution, but to keep the environment green, no other option, hydrogen, because it is less pollutant when compared to petrol or diesel. In comparison, we can have different electric vehicles. First is the battery-based electric vehicles, where the propulsion is done by the electric motor. And we have the combination of capacitors and batteries for the energy. And the advantage, we don't have emissions, or we don't going to use the oil. And of course, the battery size depends on the requirement, and they are commercially available. What are the drawback? Lithium battery is very expensive, and the capacity increases as the power of the electric vehicle increases, and the charging time is not very fast. At least 25 minutes is required. The maximum is 30 minutes, so there is not a fast charging network. And availability of recharging is also a complex, because we don't have a frequent stations, and it's very expensive. About hybrid electric vehicle is a combination of electric motor and IC engines, and the storage technologies are batteries, ultra capacitors, and IC engines. What are the main advantages? There will be emission, because it's not free of absolutely not free of fuels, and it can be applicable for long range, because it's a combination of IC engine and battery, so that capacity is very high, and it can be pumped from both fuel and electric power. And of course, this model is available commercially. What is the challenge? The energy management. Already I said you, we have an electrical part, we have a mechanical part. We need to couple both, and we need to manage with sophisticated control optimization algorithms. Is going to be a big challenge between two different sort of power supplies. And of course, the battery sizing and optimization going to be a big challenge in this case. The last one is going to be the future, the fuel cell based electric vehicles. In this case, I just put an electric motor, but also we can have a parallel operation of IC engine, but it's not perfect, because we need to have a 100% emission free vehicle. So fuel cell will be play a critical role. And the storage part, here I shown only the fuel cell, but we can also include ultra capacitors and battery, so that we can able to minimize the requirement of hydrogen or required for the electric vehicle. So it's become a hybrid fuel cell based electric vehicle, which is more attractive solution of the future. What is the advantage? There will be little emission, because we are using hydrogen, but the efficiency is very high when compared to all the vehicles, and doesn't depends on the electricity, because it's purely on fuel cell. But of course, the battery comes, then it depends on the electricity, and the price is very high, but because of the hydrogen generation, and available commercially by the companies. What are the drawbacks? Expansive generation of hydrogen. We need to find a solution to generate a cheaper price hydrogen. And about the workable ways, that's very complex, because we don't have a frequent fuel pump station for hydrogens. The infrastructure need to be developed, so the initial cost and the running cost is going to be very high. And the availability of generation of hydrogen is very important. How we are going to have a new technology which can produce a cheaper price hydrogen. The most important aspect of power electronics is shown here, and how the power electronics converters play a critical role in charging as well as driving the electric vehicle. So this is the complete infrastructure. The DC power supply is fed to a buck boost converter, which can be able to pump up the power from the battery source very high or low with respect to the current and voltage at this link. And the power generated is around 3.28 kilowatt, and which is fed to a primary inverter. And this is not a standard inverter, it's a high frequency inverter. So these DC voltages available at here, this DC link point will be converted into a very high frequency AC voltages, which is around a power generation of 3.13 kilowatt. So from 3.28 we have reduced to 3.13 kilowatt, and this is a primary coil, or we call it as a transmitter technically in case of electronics. So this coil will transfer the power maximum to the secondary coil, and the secondary coil power is around 3 kilowatt, So the converter rating is also fit to 3 kilowatt, which is AC to DC converter, which converts the AC signal into DC. And we are having a DC link coupling capacitor to reduce the ripple content which is generated from the secondary converter. And the power available in the DC link is around 2.91 kilowatt. And this power is fed to a standard 3-phase inverter which converts DC to AC, and we are driving the electrical machine. Of course, the reverse flow of possibility is available when we want to have to charge the battery systems. Of course, this is on the charging station, this part on the primary side, and the secondary part is onboarded on the electric vehicle. So from the secondary coil, it will be fit inside the electric vehicle, whereas this part going to be designed on the charging stations. If you look at the efficiency, it's most important from the DC point of view towards the primary converter, which is around 95.4% efficiency. The air gap efficiency, the power transfer from the primary coil to the secondary coil, is around 96.1%, and the efficiency between from the secondary coil to the DC link of the load side converter is around 96.8% efficiency. If you look at the overall power flow from the DC link from the source of the battery towards the DC link of the electric vehicle, which is driven the propulsion system, will be around 88.8% efficiency. The most important is the batteries, because batteries play a critical role. We can't put any batteries into the electric vehicle. There are some consortiums which governs the regulations. So EV batteries, the regulatories being controlled by Advanced Battery Consortium from United States, and there are many goals. The primary goals, the energy density. The energy density should be 135 watt hour per L. So this is the discharging capacity, and for the long term it's 300. Specific energy density, which is around 80, and for the long term it's 200. Power density 250 and 600, and specific power, which is calculated watts per kilogram, which is 150 for midterm, and for long term it's 400. Lifetime, it's for the year 5, and for the long term it's term. And cycle life, which is around 600 times charging and discharging for the midterm. For the long term it's 1000. What is the price? USD per kilowatt hour, which is less than 150 for midterm, and for long term it's 100. And the most important is the battery operating temperature, which is lies between minus 30 to 65 degree, and for long term minus 40 to 84 degree centigrade. Recharging time less than 6 hours for midterm, and long term it's going to be 3 to 6 hours. So these are the primary specifications we required for the battery. Of course, for the fast charging time, considering the factor as a maximum 80% state of the charge, which is around 0.25 for the midterm, and long term still not decided. What are the secondary goals for a battery? Discharge, self-discharge. So self-discharge should be less than 50 for midterm, and less than 15 for in terms of months for long term. And efficiency 75% and 80% for long term. Maintenance, obviously we don't have any maintenance issues with the battery, so maintenance is not required. And resistance to abuse, tolerance, it should have a high tolerance capacity, because batteries are fit at the lower deck of the vehicles, and it has to travel through rainy seasons, winter season, every temperature coordination it has to balance. So then most important is the thermal loss, which is around 3.2 kilowatt hour for midterm, and the same applicable for long term. So based on these criteria, companies use many batteries. Example, i3 vehicle, which uses the total capacity is 22 kilowatt hour, and usable is only 18.8. Efficiency is 85%. In C30 vehicle, it's around 24, the total energy capacity, whereas the usable is only 22.7, and the efficiency is 95, which is better, very good. B class, we have our total power energy is 36, and the usable is 28, and of course the percentage of usable energy is only 78%. E6, energy capacity is very high, 61.4, and the usable is 57, and efficiency is 93. RAV4 model, we have a total energy of 41.8, and usable is 35, and the percentage efficiency is 84%. If you look at all the models, two models shows a very vital perspective with respect to the efficiency. One is C30, which is having 95% efficiency, but the total energy is only 24. Whereas in C6, it is around 61.4 total energy, and the efficiency is 93%, which is a trade-off between C30 and C6. About charging stations, we have presently we don't have a DC charging stations. We use the AC we use the AC grid supply, which is from the distribution section, and then we are charging the batteries. So there are standards which is created by the Society of Automotive Engineers from United States, and here I'm giving the scales as per the standards of US, but it's same applicable for each countries. So for the level 1, it's going to be 120 volt single phase, and the current carrying capacity can vary from 12 ampere to 16. And most important is the breaker, which varies from 15 ampere to 20 under faulty conditions, and the maximum output power can vary between 1.08 to 1.44 kilowatt. In level 2, there are different categories, so the voltage variation between 208 to 240 volt, all the 3 cases in level 2, but the current carrying capacity minimum is 16 and maximum go up to 80 ampere. And about the breaker capacity, 20 is the minimum, and maximum it is decided by NEC 635 standards. About output power, 3.3 to maximum 14.4 amperes. And level 3, which is the high power, because we can go up to 600, the scales of 208, 480 and 600. And the maximum current variation is from 150 to 400, and the breaker rating current is around maximum 150, and the maximum output power in kilowatt is 3. About the future is going to be DC microgrids for all the electric vehicles, because we are focusing more shifting towards DC power wherever possible. It's not possible to have 100% DC in the entire system, because all the transmission, distribution or AC is not possible to convert everything into DC. This is very expensive and production issues are there. So in this case, we have DC charging station. There are 3 guidelines to follow: level 1, level 2 and level 3. And the voltage varies between 200 to the maximum 600 in level 3. The maximum current variation is, in the first case, maximum is 8 ampere, and we can go somewhere less also. The maximum in case of level 3 is around 400. About power, 36 is the level 1 maximum, and level 3 go up to 240. So we have a standard scaling how to have a DC charging and AC chargings. And how the power electronics converters play a critical role, because these are the various research available solutions. So first configuration is the parallel operation of a buck boost converter, because this part is a buck converter and this part is a boost converter. Combined together in a parallel operation, we can able to enhance high current to the load ESS. What is the drawback? As you know, in case of a standard buck boost converter, the factor is reduced by a value K divided by 1 minus K. So the efficiency, of course, large duty ratio variation is not possible in this configuration in universal DC-DC converters. Other possibilities, we can have dual converters. Dual converters, we can have 2 converters of AC to DC, DC to AC conversion on either side of the motor. So there is no start point you can have it. So it's the open winding permanent magnet synchronous motor, and battery is fed to the both inverters, and the power is shared equally, so that the battery power is reduced by a factor of 50%. So each inverter need to provide only the power 50%, and the total power available on the motor propulsion system is 100. What is the drawback? If one inverter fails, we need to create a start point, and the efficiency or power is reduced by a factor of 50%. Since both the converters are fed from the same power supply, we will have the same start point or neutral point. There will be a flow of homopolar components or zero sequence components obviously available in all AC networks, even in our house, which is pumped from the 3-phase system. So there will be a flow of homopolar components whose frequency is unknown. It has a multiple frequency from 0 to n number, so that this can create a lot of vibration in the motor propulsion systems. Because of that, we will have the speed pulsating, of course the torque, and sometimes it creates a lot of heating in the winding. As the day progresses, in a period of time, the winding becomes weakening with the inductance property. So other possibilities, we can have dual converters, which is fed from 2 inverters and isolated batteries. So in this case, we avoid a homopolar component because we don't have a common start point between the two power supplies. And of course, in this case, the battery power can be reduced by 0.5%, but we need two batteries. And each power fed from the converter VSI, voltage source inverter, is going to be only 50%. Again, the problem, if one converter fails, we need to create a proper start point for closing the winding on the stator. Other possibilities, we can go for a boost power factor converter, interleaved boost converter. Here it is a combination of two parallel addition of boost converter, and you know the formula for it, 1 divided by 1 minus k into input voltage, and the main power from the grid is connected through fully controlled bridge rectifier. So a fully controlled bridge rectifier obviously pumps the DC AC voltage into DC, a factor of 2 VAC by 3, obviously it will have a reduction. Then we are feeding to a boost converter. Again, the boost converter doesn't have a wide range of duty ratio, so that it suffers with the efficiency and power transfer to the load. But advantage, we can be able to keep the unity power factor on the input side. Other possibilities, we can have a dual bridge boost converter. In this case, a full bridge converter, the upper components has two diodes and lower components has active devices, semiconductor devices, which is controlled. Then it's become semi-controlled because we are not controlling the full cycle. We can control only the half cycle with one leg and another leg for the negative cycle. So it's a half controlled circuit. So obviously when you have a half controlled circuit, you reduce the conversion of AC voltage into minimal with more ripple. So the capacitor requirement in this circuit is very large. Apart from that, to control the unity power factor, we are providing a slow diode so that the return of homopolar components towards the circuit will be much slow. Because of this slow diodes, also another disadvantage, we create the operation of the control is much limited, and one advantage, we can able to keep the unity power factor here. Other possibilities, we can able to have an extended leg, and extension of this configuration, we can able to have 4 legs, top 4 diodes, which is uncontrolled device, and bottom 4 controlled semiconductor device. Then we can able to effectively control the power, which is twice the previous configuration. Again, here we need a capacitors 50% of this configuration, and controlling all these devices doesn't have a huge range of duty ratio. It's limited. So the future will be focused on resonant converters, which is operated with 0 volt switching and 0 current switching. In this case, the DC power supply, either from the batteries or from the DC microgrids, will be fed to a high frequency converter given to a primary winding, which is a transmitter, which has inductance properties with a air coupling ratio of 1:n to the secondary winding, which is bounded on the electric vehicle. On the secondary side, we'll have uncontrolled diode rectifier to convert these high frequency AC signals into DC. Obviously, the capacitor requirement is very large because this is an uncontrolled bridge rectifier, but it's a cheaper solution. Also, in this case, since the secondary side is uncontrolled, we have to compensate a large capacitor for keeping the battery safe operation with limited triple content. Same configuration can be extended as a parallel operation on the source side from the DC microgrids. We can have 2 converters coupled parallelly so that we increase the current carrying capacity double the previous configuration, and we have two separate isolation transformers or resonant transformers or resonant circuits. Then we pump the power to the load side uncontrolled bridge rectifier, and through the 2 capacitors we create the neutral point and we feed the power to the battery. So the power from this configuration will be 2 times the previous one. Other possibilities, by introducing a small capacitor on the primary side of the transmitting coil or resonant circuit, we can have an LC network so that you can have much power transfer from the primary winding to the secondary winding. That's why the ratio changes from the previous case. It was 1:n. Now it is n1:n2. We can have different winding. By adjusting the winding ratio, we can transfer high power from the primary side to the secondary side. Again, we need to discuss on the capacitor design, which is a challenge for the batteries to have a reduced triple factor for its reliability. And about I will discuss the real-time converters, which are highly applicable in electric vehicles. So obviously the buck converter, we are having an operation step down, because in buck converter the output voltage is reduced when compared to the input, and it can be operated in both the continuous as well as discontinuous mode, and this is used only for charging purpose. Buck boost converters, we can go for a step up or step down. It means that output will be large or less compared to the input, so it has a two mode of operation, and it can be used during regenerative braking. For example, when you are applying the brakes, the regenerative energy generated from your motor can be fed back to the battery. We need to have buck boost converter. Then we have looked interleaved boost converter with a power factor correction. Also, this converters helps to step up the voltage and to provide the unity power factor, but we need a small EMI filter, because in power electronics EMI is a part of a system, and we have to compensate the electromagnetic interference through filters. And here the application is for charging of the batteries. Then we discussed about a dual bridge power factor converter. Also, this used for step up, of course, for the power factor correction. And in this case, we doesn't require any rectifier on the input side, and it is used for charging. Last version we look the future is going to be the resonant converters operated with both 0 volt switching and zero current switchings. And these converter doesn't requires a AC to DC conversion, because DC link is an inverter which converts the DC to high frequency AC to the primary coil. And we adapted 0 volt switchings, and of course zero current switching is required. In case of application, it's used for charging, and these converters are very efficient because they pump the maximum power from the source to the load and keep the charge readily charged for fast charging applications. Why we are talking about all these power electronics converters? Because the future is going to be the electric vehicles, which is pumped by fuel cell. So the fuel cell, you can have a look. The fuel reformer has a maximum efficiency of 80%, where the hydrogen is stored and converted through the fuel reformer for a generation of DC voltage through fuel cells. Whereas the efficiency of the fuel cells is only 60%, and the power available at this point is not sufficient enough to drive and pump the propulsion of the system. So we need a DC-DC converter to increase the voltage. Then we need an inverter to drive the motor, and of course we may have a lot of luxurious load within the electric vehicles. If you look at the efficiency, power electronics converter boost up by a factor of 80%. That's why we are merging these the fuel vehicles, and of course with the batteries and these power electronics converter to enhance the capacity. And as I said, the future is going to be a combination of batteries and fuel cell. So of course battery is very expensive. We will put a part with ultra capacitors. So the ultra capacitor and battery can be a combination to reduce the price of the lithium battery along with the main fuel propulsion system fuel cells. So in this case also, the power electronics converter play a critical role for 80% efficiency. So in this case, we can able to pump the power from the propulsion motor through a DC-AC converter and fed to the battery or ultra capacitor for charging and keep the power, and it can be pumped back to the driving units whenever it is required on the demand. So it's like an opportunity to make a bidirectional power flow from the batteries and the load propulsion systems through power electronics converters. If you look at the large scale transportation system, obviously we can't do with absolutely full battery system. So we need a fuel cell, which is going to be the main powertrain system. And within the electric vehicle, we are going to have a DC microgrid, because the power requirement is very large. The battery capacity is around 600 to 700 volt, and we need battery charging controlling units, and these are onboarded within the systems on your right hand side. On the left hand side, we are going to have a AC load which is around 20 kilowatt. So AC loads means lights, etc. Luxurious needs within the electric vehicles, and many applications are AC in large scale transportation electric vehicles, and these are pumped through a standard inverter, because we are getting a DC link, DC voltage, it has to be converted to DC. And we have again another converter which converts the DC to AC for the propulsion of the motor through motor control units. Then about the luxurious loads, there are a lot of luxurious requirement within the electric vehicle, which is around 25 kilowatts. For example, a large scale transportation vehicle for commercial purpose, then this is requirement 25 kilowatts. Again, it is formed from the fuel cell through a DC-DC converter. So obviously the efficiency can go guaranteed around 80%. What we have done for these applications, it's from the own research groups. So if you look at the standard microgrids, we can get the power from the PV, wind, batteries through different power electronics conversions. So first case, we need a DC-DC converter to match the power from PV to the DC microgrid. Then for the wind, the power conversion is to be done from AC to DC. Then we need to DC to high up the power to the requirement of common point of coupling. Then we have a battery through DC-DC converter in a bidirectional mode. We can pump the power from the grid to the battery or from the battery to the grid. And the load can be charging at DC electric vehicles and of course any AC loads. The standard configuration and total converter requirement is around 4. So this can be optimized by introducing new power electronics converter, because here only for the windmill we need to convert the AC to DC, because all the windmill are coupled with AC machines. It's a double fed induction generator or synchronous machine. The power generation is AC, so we need to convert it into DC and then fed to the multi-port converter. Then we can able to pump the power to the common point of grid and with the same applications. So in this case, we have shown here a multi-port converter with 3 ports. Port 1 is devoted for the PV power, port 2 is for the battery, and port 3 is for the load. And this configuration is developed based on a standard combination of buck converter and a boost converter. By adjusting the diodes, the flow of current is controlled and we can able to manage the power very effectively. As we know, PV, battery and wind doesn't going to have the same power. There is a fluctuation, huge fluctuation. So in this case, the power electronics converter need to maintain the constant power requirement to the load. That's why we are going for maximum power point tracking. So the goal of the power electronics converter is to keep always the power at the maximum point, irrespective of any deviation or fluctuations from the power sources. For example, if the power from the PV is moving towards on your left hand side, the power electronics converter controls the duty cycles, switching triggering time of each semiconductor devices and bring back to the maximum power. Similarly applicable when it's moved towards the right. These are some of the experimental results what we got at a prototype model, not going for very high voltage for the safety reasons. So as like for the application of electric vehicle, we consider it as like a battery. So 12.5 volt is being taken from the PV. Current is around 7.9 ampere and pumped to the load with 24 volt. It's just doubled. And the load current requirement is around 3.6 ampere. And if you look at the PWM generation from FPGA based solution is very effective. The most important is the current, because the current through the inductor decides the reliability of the batteries. Of course, the load connected propulsion system, the motor, to have a fine speed and torque without any pulsations. If you look at here, there is no any short spikes or huge deviations, and all the ripple factor are within the standards of IEEE 512. And we tried only for 60% of the utilization of the DC power, I mean from the photovoltaic. In the second case, we were trying at 40%, but the operation is just vice versa of the previous one. So we keep the power on the PV maximum to 30, and the current pumped from the PV is around 800 milliamps, whereas the load is only 18. So we just vice versa. The load now getting the less power, whereas from the PV. And the load current is around 980 milliampere. Again, the same way we have shown the characteristics of the current through the inductor, which is very important to maintain the ripple factor, of course, to govern the reliability of batteries and PV, which is connected to the system. How we executed all these experiments, that's most important. We tried first in a numerical model. In the numerical model, the efficiency shows pretty good. It goes near to 98%, because it's an ideal environment. We didn't consider various losses. But in real time, the efficiency goes maximum 93.6%, considering all the switching losses, conduction losses, and of course passive effects and EMI effects. How the algorithm is developed? So we have the proposed converter, and we have since the parameter of voltage and current from the PV, current and voltage from the battery, load current and no load voltage. All parameters are given to the multi-objective controller. What the decision the multi-objective controller will do? It will generate the duty cycle, the triggering time for all the semiconductor devices, mode of operations, battery management, how the power flow needed to be done, either from the battery to the load or load to the battery, or from the power electronics converter to the battery. It's an idea. So what is done here? Simple solution. We start the program. We check the power of the PV is greater than 0. Yes. Then we go to the next step. We are checking the power of the PV is max greater than P naught. Yes. Then we go to the next step. We are checking the battery current. The battery current is greater than the battery current maximum. Then we connect the PV to the load. If fails in the first step, we connect the battery to the load because the PV power is not sufficient, so we want compensation from the battery. If it's fail in the second case, we connect because the power is not sufficient from the PV, but it's greater than 0. I mean, a 50% power is available from the PV, then we add the 50% of the power from the PV and 50% from the battery and connect to the load. If it's fail in the third step, then we are checking for the state of the charge is 90%. If it's 90%, no problem, we connect to the load. If it is less than 90%, then we connect the PV to charge the battery, then we are connecting to the load. This is a new configuration we developed for a large scale DC application, and it has been patterned in United States. We are expecting any time to get the approval. If you look at the load side, is a standard boost converter, standard classical industrial boost converter. On the source side, what we have done, so this part is a standard half bridge converter where one of the semiconductor device is replaced by the inductor, and we introduce an additional leg again with the MOSFET and one inductor and capacitor. What is the purpose of this capacitor? Is to store the energy generated from the inductor when the device is closed. So when the device is closed, the instantaneous energy available in the inductor will be transferred to this capacitor. So we're going to get a large power, and this will be given to the input of the boost converter so that large voltage can be generated. And these legs can be extended to N level for the requirement of your load application. So we had tested this converter in a very low profile prototype because for the security purpose and of course for the safety and the cost optimization. So we tried between 100 to 500 watts. In case of experimentation, we got around 93% efficiency, whereas in simulation it goes near to 97% because we didn't it's considered under idealistic parametric values. And these are the applications. We can have a very large power supplies applications with a DC microgrid with a common point of coupling around 400 volts. Here we can charge the electric vehicles. The future is going to be pump the power from the electric vehicles to the grid so that every electric vehicle owners can be an entrepreneur to gain some margin from the grid operators. Of course, we can pump the power from the PV to the microgrids. Then for the home applications, so almost our home application like a mobile or a laptop, iPad, everything is DC power supply. But we get the power from AC grid single phase, we convert it into DC and we are pumping. So the intermediate adapter is a DC-DC converter, is a SMPS, switch mode power electronics converter. So of course we can pump the power to DC-DC converter directly. In the future, if we consider DC home as a smart city projects, then we can have a power electronics converter which can step down the large voltage from 400 to the requirement of 24 volt or 12.5 to the each houses. Of course, we have on the right hand side the transmission system. We are not going to change the existing transmission system of AC. We want it because it's very expensive. We can't change it to complete DC. It can be coupled to AC voltage regulator, which is an anti-parallel connected thyristor. Then to AC to DC converter, we can couple to DC microgrid. Of course, large power is available in Denmark from windmill. It can be coupled through AC to DC, DC to AC conversion, then to AC to DC to couple DC microgrid. And capacitor battery bank is essential because during the peak power generation, it can be stored in the batteries. And during the peak demand of the load side, we can pump the power from the battery to the DC microgrid. So it's an optimal solution we can handle in a sophisticated way with modern artificial intelligence technologies so that the energy optimization, of course, the management is very effective. And these are some of the experimental and numerical results what we got from the testing. So we try to keep the converter with a very minimum input voltage of 40, and as expected, the load voltage is generated around 400 under ideal condition, and the current is around 1.4 amperes. And this is very important. The current through the inductor is very smooth, and there is no short spikes which can affect the input batteries or of course the load connected electric vehicles motor, so that very smooth operation. And we find the same response in the experimentation, but the input voltage is kept exactly 40, but the output voltage is not 400, it's 394 volt because there is a switching loss, conduction losses, other losses is compensated. Obviously, the current also reduced when compared with the simulation accordingly with the load. And these are very important parameters of the voltages of the capacitors, because capacitor reliability is a separate research in power electronics, how to have a very strong capacitors. So with a sophisticated digital system, what we used, FPGA, doesn't have any short spikes, and the transition between the upper limits and lower limits, which is technically called as a ripple factor of the DC voltage, are very limited as per the standards of IEEE. And this is the generated voltage. As I said, we are maintaining the constant value, and the current through the inductors are optimal, and we ensure all the factors are governed for the proper IE standards of IEEE 512, IEEE. Of course, these are the simulation model that we got the same value, but in idealistic factor, because we are not concentrated on the losses in the simulation. What will be the future challenge for electric vehicles? How we have to focus our future with all these engineering advancements. Efficiency, yes, most of the mechanical parts in your electric vehicle needed to be replaced. For example, in the past we use a hydraulic system for ABS systems for the protection, but now it become change small power electronics converter called actuators. The small DC-DC converter, we are controlling ABS and airbags available in the electric vehicles is the renovation. And of course, in case of perfect combination is required between PV and fuel cell and battery, so that the system is much optimized, cost optimize the system to power management between the PV, fuel cell and battery. Of course, the efficiency mainly depends on electronics component selection, control strategy, how we are compensating the EMI effects. How to increase the durability of the renewable, and of course, for the EV application, the most important is the battery, because it's the most complex part of the battery and most expensive. So we need to design a proper electronics converter which can able to pump very minimum ripple content with very fast perturbation for the requirements of the battery. So it can increase the battery lifetime as expected with the design. So the goal is to have a proper charging and discharging through power electronics converters. And the lifespan again of the battery depends on the selection of semiconductor devices, how we model the power electronics converter. Apart from that, the power electronics converter has to withstand high vibration. If it is a windmill application, huge rotation of the blades of the windmill has to be observed at the large scale wind operation. Of course, in electric vehicle, a lot of vibrations. So we need to have a proper vibrational arresters for power electronics converter. Obviously, the current through the power electronics converter will be very large because they have to maintain parallel many parameters in an electric vehicle. So we need to have a proper thermal isolations and cooling systems. And obviously, the challenges lies for high efficiency, rigidness, low cost, small size, and to give maximum luxuries to the customers. How to increase the performance of the renewable? Obviously, the next factor is the digital signal processor. So the digital signal processor, what you select for the electric vehicle applications, should be much faster with the sampling. It should perform the pre-programmed instruction in a timely manner to execute the actions. Obviously, how the safety can be increased. So we need to adapt sensors. Modern sensors are focused on a IoT based Internet of Things, because we don't want to have a cable connection between the digital processor and the sensor. All the parameter will be transferred through Wi-Fi. So obviously we need to keep the sensors in the stator, rotor and bearing to avoid the faults. And in case of, as I said in the beginning, EVS system, AVS, airbags, etc. Now it's replaced by a small actuator called DC-DC converters. So it's very compact. Even under the failure condition, we can able to replace this component much cheaper. Again here, the safety requirement always plays with how fast, how your digital signal processor evaluate all these artificial intelligence techniques, and of course how it execute, how it diagnose, and how it can able to prevent the scatterscopies require when happen within the traveling population of the electric vehicle. So all depends on the sampling, how much faster sensing units. It's very important. How to reduce the overall cost? That's most important. The overall cost again play a critical role with the component selection and how to select the appropriate renewable energy systems. At the same time, we have to balance the luxurious needs within the electric vehicle. So the challenges always in electric vehicles for the selection of electronics components, how to reduce the cost of the hydrogen production, how to optimize all with respect to the reliability and high quality performances. Conclusion, The future of the electric vehicle is going to be a fuel cell based combination of battery electric hybrid model. And the most important challenging task, I said, how to reduce the cost of production of hydrogen. And of course, the battery technology, now we have lithium battery, but it's not a prominent solution because of the expenses and recycling properties. So how to recycle it? So in the future, we are looking for the replacement of batteries by ultra capacitors, and of course, other technologies are available. It has to be enforced to reduce the cost. Of course, the size, that's the challenges when compared to the battery. Other technologies are huge in size, and of course, we have to uh, mitigate all these problems associated with the generation of harmonics. When many converters, many renewable are coming to the picture, obviously there will be unbalance on all this has to be compensated. Of course, we are working more on wireless technology, but it's not commercially available until because it cannot be adapted for very high power application. So wireless charging technologies are for medium and low power application. As I said, we have to concentrate more on the stability issues. As the number of electronics converter increases, as the number of renewable increases, then the stability become a question with the harmonics, voltage sags well, and the grid need to be smart enough with grid supported converters. So we need to adapt AI technologies to predetermine in advance, diagnose it, and take a self-recovery process without human efforts. Future is going to be again a vehicle to the grid communication and grid to vehicle communication with smart meters, and this is a big challenges we are going to face and to gain the margin. So each electric vehicles in the future going to gain the margin from the grid, and the research also focused on energy management to have an optimal charging of batteries. And obviously there are many artificial intelligence techniques needed to be adapted. This is also a bound of increase in research and many challenges available. Thank you one and all for your attention. If you have any specific questions, I'm happy to respond.
Thank you, sir.
Yeah.
Thank you very much for your very nice presentation. And moreover, I would also like to thank you for accepting my invitation to join the workshop in such a short period of time. So I hope the session was very interesting, and the session we have learned a lot. Okay, so if the participants have any questions to share, they can ask sir now. Now, over to the participants. Please ask sir if you have any doubts in it.
Good afternoon, sir.
Hi, good afternoon.
So it is not actually a question, but a comment. If we are I am a mechanical engineer from Symbiosis, and your presentation was like a hurricane for us. You started and finished. It went up so fast before you catch it, it's over. So though because we don't have the basics of the electronics and circuitry, so might be we are lagging there. But it was a good presentation, sir. Thank you very much.
Thanks a lot. Any more questions?
Amit,
Sir, one
Onu
question,
and Amit,
question, sir.
sir. Yes.
Sir, may I, sir?
Yes, definitely you can.
Sir, question regarding this wireless technology which we are mentioning. You mentioned only in one line. Can we know exactly what is the status of wireless charging and when it can be possible on ground in India? When can we have this wireless charging for the batteries? What is
So,
the status of
at
this?
present, I think only country which has tried the wireless charging station is China, but it's a contact-based wireless charging. I mean, they have a track, and the vehicle has to travel along the tracks. So, because between the air gaps, the power can be transferred continuously and it can be charged. But it's a very expensive technology because, as I said, I given you a model because I didn't talk because this is a separate topic. There are technologies. What are the technologies? If you look at this is a simple example how I showed you the wireless charging mode, because this part is the onboard on the electric vehicle, the secondary winding, and the primary winding will be fixed on the charging station. So this is the charging station, and this part is going to be on the electric vehicle. And if you look at the transfer ratio is very good, 96.1%, but the overall efficiency down. So we predicted only at the power transfer from the DC source to the DC link of the load side converter of the electric vehicle. So which is around 88.8%. But from here again the efficiency will go down, maybe 72%. So the major drawback in case of wireless charging station is the efficiency, and the other possibilities are more expansive to develop these technologies with for example, the charging through cruising is very complex. Then we need to have tracks. We need to create a new tracks. And countries like our India is very complex under more thickly populated. Maybe for the highways is very good, but not for the rural, or I mean for the areas which is located more densely populated. For the highway is a good option, but most expensive. So there are some technologies which is available in China. They tried, it is working, but still the efficiency needed to be improved. That's why I explained you we can have such converters. I explained you very well during my presentation, and these converters plays a critical role in increasing the efficiency from the source to the load side of the battery. So these converters are wireless technology based converters, because we use a coupled inductor, and this part will be mounted on the charging station, and this part is the onboard mounted components of your electric vehicle.
Thank you.
One of the participants have asked you, sir, could you please explain the voltage doubler principle in your slide show?
For example, I can give you an example here, because the voltage is doubled from here. I'm right, from 12.5 to 24 volt. So in this case, what we are doing, we have a PV panel, we have a battery, and this is a standard buck converter. Why we keep a buck converter here means to keep them. So buck converter is like a current controlled converter. So we keep the current here and the voltage minimum. But by the adaption of boost converter here, we increase the voltage, because here it is connected with the PV panel, and here we are connecting with the batteries. And this combination, when we are adding up, theoretically we do the circuit analysis. In the circuit analysis, we derive the equation. From the equation, it will become 2 divided by 1 minus k. So we double the power of the power conversion from the source to the load. It's an example. Another example I can give you with the same experimentation. For example, the load side converter. If you look at the basics of electronics textbooks in your library, you can find the formula. The formula is going to be 1 divided by 1 minus k. It means k is maximum, can go up to 0.9, but we don't use 0.9, we use only 0.6 or 0.75, because for the marginal and in order to protect the devices, we keep the margin. So the formula requirement for is 1 divided by 1 minus k. How I can able to increase, double it? So that's why we adapted these converters. So this converter will adapt and helps to increase the voltage level at this point by a factor of 2 into k plus 1 divided by 1 minus k. So you get a very large margin power gain by adjusting the power electronics converter and doing some circuit analysis based on Kirchhoff voltage law and current law. Then we find these equations. Any questions? This is a simple example. Here the power is 1 by k. If I increase the power here, I will get double here. So for increasing double, I use this power electronics converter.
Question is being asked, sir. Also, could you please explain about the slow diode in figure 9? Could you please explain about the principle of the slow diode in figure 9? One of the participants have asked you, sir.
Yes, this is to control the power factor here. For example, when the grid are much faster, instantaneous, and then the semiconductor devices, because semiconductor devices we are controlling using DSP or FPGA. For example, if you are using a DSP TMS32F2812, the maximum instruction, 150 million instruction per second can be executed. But grid is, we can't predict it's instantaneous value, it's very fast. So when we are controlling the grid, we need to provide a slow diode. A diode is obviously a slow factor because it is not controlled. It is not controlled. So obviously we are controlling the current fed to the grid through this diode very slowly, optimally, because then we have the freedom to control the unity power factor on the source side. So we want to keep the unity power factor unity, then we need to control the current here. So in order to control the current, we are putting these diodes, so the response will become little slower when synchronizing the grid with the power electronics converter. Any questions?
Over to the participants. If anyone do have any questions, you can ask sir now. Okay, sir is very busy actually, but still we have given up the time and consent for this workshop.
Hello?
Yes.
Yes.
Yes, sir, in the starting slide, in the AC charging, level 3, I think the power is written 3. Can you, sir, go to that slide? The AC charging level 1, level 2, and level 3.
Yeah. This is US standards, not for adapted. For India, we have to change into 220 volt or 240 volt according to the requirement. So this is the standards given from the Society of Automotive Engineers.
So the power will be limited to 3 kilowatt only, or
For a single commercial home appliance electric vehicles. Because again I tell you, a battery cannot completely replace the requirement. So these are the standards. So they have to design an electric vehicles with the standards, keeping the current maximum and the balancing the power of the voltage. Because in electric vehicles, the batteries are 48 volts, not 1000 volts.
no, sir, I am asking level 3. Level 3 charging, the power level will be written to 3 kilowatt. So is it
The
correct?
minimum requirement, the minimum requirement.
Minimum will be 3. Okay.
Yeah. We can't go less than this
Thank
one.
you, sir. Thank you, sir.
Maximum we can't design because maximum can go up to any value, because if you want to follow the guidelines of this, we need to have a minimum 3. So with the short circuit braking, 150 amperes, with the maximum current rating ranging between 150 to 400 amperes, then we have to choose only 3 kilowatts, the minimum standards. So now we have the guidelines for 3 kilowatts, you can extend for 6. According to, because the power capacity is decided on how many vehicles you are going to charge. You are not going to charge one vehicle, n number. Then depends on the capacity. We need to know the capacity, then we can increase the power accordingly. It's a minimum requirement. Any more questions?
Once to means
Sir,
one
another
participant
question
have
is
asked you. Yes, please.
Hello? Yeah. So the question is that now it is the concept is coming vehicle to vehicle charging. It is coming under dynamic wireless charging. So what can be the power limit for that type of charging infrastructure? Vehicle to vehicle charging.
Vehicle to vehicle charging is under autonomous vehicle concepts, but again the concept lies with this factor. The big challenge is this part, the distance between the two coil, between the two vehicles. You can have, for example, one vehicle is in 1 meter, still we don't have a fast charging network. All the networks which is having a wireless charging are very limited, maybe less than 50 millimeters centimeter gaps. That's very important. So this part is the challenge, not this part or this part. How you transfer the power by contactless? We can't have an infinity distance. It's not possible. Until now, there is no technology can transfer the power for 1 kilometer gaps. So it depends. So these converters, so then two vehicle has to travel very closely for the dynamic charging of transferring power from one vehicle to another vehicle. So it's a challenge. It's maybe in the research, but the realistic factor, it's very complex. And of course, how much, as I said, you can see the simple example I showed you. the efficiency, what happened? 96%. It's the same concept for dynamic charging of vehicle to vehicle, because we need two coils. That is a simple concept. Either side, the vehicle 1 will have the same concept, vehicle 2 will have the same concept. Only the coil going to decide the power transfer. The power transfer in the vehicle is very good, 96.1, when this distance is very, very, very minimum. When the distance increases, this efficiency will come down, then you lose this efficiency.
Thank you, sir.
Yes.
Because if I want to talk on wireless charging, I have different slides and different converters for that. So that is a different presentation. If you want, I can open it, but it depends on your requirement, but also the time factor.
So, thank you, sir. Thank you for a nice presentation. I feel one of the participants, Shreyas, okay, so he has asked you, sir, what will be impact on grid due to V2G and G2V technology?
I already given in my
yes, slide. You have already shown it, sir. Yes. So
also
I feel this
in the conclusion
question,
also I disclosed this will be a big challenge. Voltage instability, harmonics,
exactly.
When you connect more electronics converter to the grid, you pump more harmonics. So it's like a pollution to the grid in general terminology, and you create instability, because I already discussed here with an experimental results, because we have different power can be fed to the grids. Then different power has its own capability of generating the power. Then you create an unbalance. So all these unbalance has to be controlled by power electronics converter. When you make the power electronics converter to behave for multiple tasks, it generates a lot of harmonics to the grid and create voltage instability.
Exactly, sir. So thank you, sir, for your very nice presentation. And moreover, I also get sometimes surprised to see that each and every day you do put your papers, and I have seen that you do publish ACI papers each and every day, actually. So it is very surprising, sir, actually. Means from my side also, it's very nice, actually, sir. But my question is, sir, means how is it possible for you, for a single person, to do so much research in a particular small span of time, sir?
Thanks to my, first of all, I'm interested in it. I devote time for that. Second, thanks to my family, they also support me. Then most important is the institution. They encourage us to do many activities. Last not but the least, most important is my PhD students, postdoc researchers, collaborates, and the big network. That's why we are productive. So I say it's not a single man output. It's not true. It's a team effort. It's a dedicated researchers' minds and their devotion towards the concepts.
Exactly. Means sir has over, means for the participants, I would like to say that just now I have seen that sir has over 800 publications in his name in such a small age. Means very young also. Okay, 850 publications.
Many peoples in the world, because you are looking at me. There are many.
No, that is true. That is true, sir.
So still I need to travel many long distance, and hopefully.
Exactly, sir.
Thank you one and all for the best compliment.
Thank you very much, sir. Thank you very much. Okay, sir. Thank you.
Thank you one and all. See you all. Bye.
Bye, sir. So hope it was a very nice session. I hope so. Over to the participants.
Yes, sir.
Okay, thank you. So stay tuned for the next session, which is going to occur at 2:15, I feel. Okay, the next session will be from 2:15 to, I feel, like 4 o'clock, and from 4 o'clock there will be test, and after that there will be the felicitations Perimani. Okay. Thank you very much.
Thank you, sir. Thank you very much.